Welcome back, pre-calc students, to Unit 11 on vectors. Today we're going to do days 5 and 6 notes, Introduction to Vectors and Vector Operations. Before we get started, we do want to make one correction. When we were in our day 3 topic on law of cosines, we did make one slight error at the very end. Area of a triangle equals 1/2 AB sine of C, not cosine of C. So when we use this corner of 5, 7, and 22, it should have been A equals 1/2 5 times 7 times sine of 22, which gives us an area not of 16.3, rather of 6.6. My mistake. Want to make sure you guys kept on your toes. All right, now on to day 5. We won't do our warm-up. We just got started with that stuff, so we'll move on to what is a vector. A vector is something that is represented by two measurements. Not only a segment's length, but also where it aims. Up and to the left, right, what have you. So more formally, a vector is a quantity such as a force, a distance, a velocity, but it's described by both a magnitude and a direction. Magnitude being the length, direction being the angle. We're going to draw them like rays because the arrow is going to represent which direction it's going, but it's really a segment. It has a finite length. And we're always going to start our vectors at the origin. Okay? Like I said, magnitude stands for length. Direction is angle. The symbol for these two we're going to use most often. Magnitude is a double bar absolute value. The symbol for a vector is oftentimes a single letter, sometimes two letters, with an arrow above it. So that right there would say, I want the magnitude of vector u. Direction, on the other hand, is usually the angle theta, and you usually put a little subscript down there. That would say I want the angle of vector u. All right, so let's first start out by creating some vectors in what we call standard form. Vector PQ says it starts at P, it ends at Q. In this case, the vector is going to start at 2, 3, and it's going to end at 5, 7. That vector right there is vector Q. PQ, pardon me. Okay? Now, we can find the magnitude a bunch of different ways. We could use old Sleepy Owl from geometry. We could also use the Pythagorean theorem and count boxes. That's 3, that's 4, so we would all know that the magnitude of that vector is 5 units. And by using that same triangle, we can figure out what the direction of that vector is. That would be this angle right here. Because again, the x-axis over here would be 0. So I would say, without using the 5, tan of P equals 4/3. So P would equal tan inverse of 4/3. So P is 53 degrees. So that vector can be named by starting at P, ending at Q, or it can be named a magnitude of 5 and a direction of 53 degrees. They would both describe the same vector. Now, that creates a lot of differences. Instead of allowing vectors to start and to end at any point, we're going to call, standard position or component form. That's where this symbol comes in. And what it's always going to do is it's going to start at the origin. So, we're going to take this first vector, RT, starts at -2, -5, pardon me, and terminates at 4, 3. I'm going to try to be accurate with this vector. Because what I would like to do with it is move it such that the starting point, R, is actually the origin. Since I have the availability of a smartboard, I can simply do this. And what I would then be looking for is, where is the terminating point? And we can count boxes and go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So that point is 6, 8. How we would write that is pointed brackets. So in this case, vector RT is the vector 6, 8. What that means with pointed brackets, it's not a point. Rather, it's a vector that starts at the origin and ends at point 6, 8. And notice, this vector doesn't change. It's still the same magnitude and same direction no matter where we place it. It's going to be an easier convention to place it at the origin. Hence, it could get named by 1.6, 8. And therefore, if we have it in component form, we can now find its magnitude because the x-axis, the one leg, is the x-coordinate. The other leg is the other coordinate. So what we can simply do is use the Pythagorean theorem, or take the square of each of the legs, add them together, and take the square root. That vector is 10 units long. And to find the direction, we can take the tan inverse of y over x. And again, that works out to be about 53 degrees. So, what's the rule we're going to use to get a vector in component form? We're going to simply x terminal minus x initial, comma, y terminal minus y initial. That would have been 4 minus -2, 3 minus -5, would have given us 6, 8, without having the visual of the graph, just doing it numerically. 6, 8, distance formula, tan inverse y over x. So let's put this all together. A component form vector u, written as pointed brackets xy, starting at the origin, ending at xy. Its magnitude is simply the square root of the sum of the two components squared, and the direction is simply tan inverse of the y coordinate over the x. 3 great tools for our vector toolbox. All right, so we're going to take vector u, 1, 4, find its magnitude. We're not going to draw them. 1 squared, 4 squared, 16 plus 1, radical 17. Tan inverse of y over x, tan inverse of 4 over 1 equals 76 degrees. Vector u, you take a second, figure it out. For vector v, the magnitude is 4 squared plus -5 squared, radical 41, which approximates to 6.4. Tan inverse of -5 over 4 is -51. However, we might have theta with some constraints, and that is falling between 0 and 360. -51 is a fourth quadrant vector, so 360 minus 51, I like 309 degrees better. So vector v can be named 2 very different ways and describe the exact same vector. Pointed brackets 4, -5, starts at the origin, goes x4, y -5, or a magnitude of 6.4 with a direction of 309, describe the exact same vector. We know how to go from component form to magnitude and direction. How do we go from magnitude and direction to component form? Well, let's see if we can figure this out. If I wanted to find the component form, and I knew magnitude and direction, that means I would know this angle. Let's call it 30 degrees. I would know this magnitude. Let's call it 8. The component form would be I need to know this and I need to know that. If I created an equation using x, I would say cosine of 30 equals x over 8. So x equals 8 cosine of 30. Another equation for y. Sine of 30 equals y over 8. Y equals 8 sine of 30. So in general, what can we say about a vector when it's given in component form? No, pardon me, when we want to find it in component form when given magnitude and direction? The x-coordinate is equal to magnitude cosine, and the y-coordinate is magnitude sine. All right, so let's do this one right here. Let's change it up since we just did a 30-degree angle. I guess we can keep it. If I picture that in my head, I would say it's 4 units long. That's the angle. Where is that terminating point from the origin? For cos 30, for sine 30. If I wanted to keep it in radicals, exact, I know what cosine of 30 is, radical 3 over 2. I know sine of 30 is 1/2. So therefore, the component form of a vector whose magnitude is 4 and direction is 30 degrees is 2 radical 3, comma 2. Take another one. Take a second. Again, picture that vector. It is 6 units long. It has an angle of 118 degrees. Hence, it's a second quadrant vector. What should you have? You better have a negative cosine value and a positive sine value, a negative x and a positive y. How do we find our component form? Magnitude cosine, magnitude sine. To the nearest tenth, I got negative 2.8, just what I expected, 5.3. So we now know how to start with magnitude and direction and to find component form. And we also knew beforehand the other way of how to start with component form, finding magnitude and direction. All right, let's move on a little bit, a little more vector work. Okay. We'll skip this warm-up. Sometimes physics folks like to write vectors not in components, rather they're horizontal and they're vertical. Horizontal is simply the x-coordinate. Vertical is the y. But instead of writing it as an ordered pair, they write it in IJ notation. So in other words, vector v, 4, -9, has a horizontal component of +4. It has a vertical component of -9. So it can be written as 4i minus 9j. Me personally, as you will probably throughout this unit, if we're given a vector in IJ form, we'll convert it back to component form. Much handier. All right. Now that we know how to create a vector, how to put it in component form, how to find its magnitude and direction,